Morning, all of you. So let me start by a few of my favorite sentences before we go to the lecture. The important thing is that, you are not here for me, but I am for you. Okay. So it's for you to take advantage of whatever I can sort of, teach you or whatever you want to say. So please feel free to ask questions. It does not mean that I can answer all the questions, but that's a part of the game. Not everyone knows everything in the world. Okay? Every knowledge is limited for all of us. So, but we try to make an attempt to answer all the questions. So please feel free to ask all the questions whenever you feel. Please interrupt in between. Just raise your hand if you have any questions, and I'll come back to you and try to answer when I finish the sentence or in between, when I get a little gap. The second thing which I wanted to tell is that I am an experimentalist, and probably you'll realize that the experimental way of or experimentalist way of looking into things is very different from a theoretician way of looking into things. In science, both are absolutely essential. So as it is important for us to understand the basic physics from theoretical point of view, and that's what all the physics is about, but then we have to deal with realistic matter, and if you want to make it useful, okay, many times we are dealing with systems which are not ideal systems. In fact, most of the time we are dealing with systems which are not ideal systems. And therefore, to develop a proper theory of many of those things, that the type of work that we are doing is not all that straightforward. And many times theoreticians have to follow experimentalists, especially in this particular thing, because if you observe a phenomenon which is not clearly understood, theoreticians have to work about it. So that's what I want to say, that if you are hardcore theoreticians, you may find some of my talks disappointing, which often happens with me. Say, well, you have taught nothing. So it's okay, probably I have not taught nothing, but it's all right. But there are certain things which are important for us to know, even if you are a theoretician. At least you should know the data on which you are relying, how reliable is that data. At least that much you should know, before you start doing that. Okay. So with this small introduction, I would like to sort of go ahead. See, the school is supposed to be on magnetism, and magnetism is supposed to be one of the oldest phenomena known to people. Even in very, very old time, people used magnets to navigate. You are moving in sea and all the directions look equal. You can see the entire symmetry of the world there, and you do not know in which direction you are going other than sunrise and sunset. Okay, you have to navigate, and in that case, compass has always been used. What is very interesting is that the theory of electricity and theory of magnetism have beautiful similarities and beautiful dissimilarities. There are many things which are identical in them or similar in them. Identical is not a good word. And many things which are very, very different from each other. And somehow they are always taught together, thanks to Maxwell's or probably even earlier scientists. One thing which is very similar, like electric charges, is that like charges repel, here also like poles repel. Like unlike charges attract, here also unlike poles attract. This is similarity. But there is a dissimilarity. Charge you can always isolate. You can always put a charge somewhere without bothering about if there is a pair charge, negative charge anywhere else or not. But unfortunately, at least till now, you cannot isolate poles. If there has to be a north pole somewhere around, there has to be a south pole. So in that sense, it's dissimilar, but there's a sense in which it's similar. Now there was a time, I remember my high school days, when we had textbooks in which people will introduce magnetism exactly like electricity, like you have Coulomb's law, and you start about forces between charges. They will start with forces between poles. That's the way old traditional books have been written. But soon these concepts were totally revised and magnetism was taught in a different fashion altogether, because the poles were not considered as fundamental as charge. But what was considered more fundamental towards magnetism is a moving charge. So that's what made the difference. And now we talk of magnetic forces in terms of currents rather than in terms of poles. That has been a major difference of how magnetism was being taught over the years. Now, as I mentioned that these are forces, later came the concept of a field. Starting from forces, initially we were talking only about forces, which looks somewhat a philosophical concept, but it has a deep-rooted physics meaning. Especially when you go to relativity and things like that, these concepts become very, very important. The basic difference, as we explain normally in high school students, or let's say first year BTech students, I'm sorry I'm starting right from basic, but that's my style of teaching. I'll always start from the most fundamental aspect. Is that, suppose there is a charge here and there is another charge there. There is a force which is being experienced between them. Now suppose you remove this charge or add a certain charge amount to it. What happens whether the other charge immediately experiences that charge has changed at this particular point and the force should change immediately. This does not really go well with special theory of relativity, which says that information cannot travel, any useful information cannot travel with speed greater than the speed of light. This is only one of the arguments. But even philosophically, it appears easier to think that once you create a charge, whether there is any other charge nearby or not, there is already a field which is created in space. Okay? Only that particular field can be experienced when you put another charge. For example, whether we are here or whether an object here or not, okay, there is always a gravitational field. But on the other hand, when you put a mass, then you can feel the gravitational field. There is a force on that particular thing. So now we talk in terms of field. These days, everything is talked in terms of fields. Now, like in normal mechanics, the basic question is that when you apply a force, you want to look at the motion of the particles or rigid body. Here, when we talk about electricity and magnetism, when you are given charges and when you are given currents, you are supposed to know about what happens to the fields. That's what becomes basically the problem. Now, one of the basic laws which governs the field, as I said, now when we are talking about magnetic field, we are talking in terms of current. We are no longer talking in terms of poles. We first talk about field due to a current carrying wire. Okay? And then we talk about poles later, because whatever you say pole is inherent, because when we are saying poles cannot be separated, we are definitely talking about poles. Okay. So there is a famous law which probably all of you know, Biot-Savart's law. I will try to send the notes, I'm not sure how fast, handwritten notes on these things, but it takes a little bit of time for me to write, so I'm not sure when. So you need not spend time in writing, it's better to understand, but if you want to write, you are most welcome to write. There's no restriction from my side, which essentially tells you that if there is a wire which is carrying a current I is supposed to be a vector. Okay. However, if you look at Griffith's book, which is the most common textbook all across the world, he writes very, very boldly, current is a vector quantity. And a lot of people had an objection, and if you look at the website of their university, Griffith has given a big explanation on why he thinks that current should be treated as a vector and why others don't think. And then he says, it depends on you whether you want to treat current as a scalar or current as a vector, but I feel current is a vector quantity. Anyway, as far as normal physics tradition is concerned, current is not a vector quantity, current density is a vector quantity. Okay, but we always show a direction to the current, and that was his argument to show that current should be written as a vector. But whenever we have in Biot-Savart's law, etc., always we have also a direction representing thing. Even if I take I as a scalar quantity, there is always a dr or a dl term which defines the direction of the current, okay, whatever it is. So it shows that B, if you take an element dl on this particular thing and look at a particular point and want to find out the field at this particular point due to this particular small element which is carrying a current I, then you have to look at the vector R here, and this Biot-Savart law gives you what is the field which is going to be there because of this particular current. So this is given by mu naught upon 4 pi, as you know, I dl cross R upon R cube. If you are writing vector R, it should be R cube. If you are writing unit vector R, then it should be R square. That's what is the Biot-Savart's law. So this tells you, and of course you can integrate it over the wire to get the entire field due to the wire. I mean, whatever way, if it's a closed wire, it's open wire or whatever, you know, there are a lot of problems which people do in higher scaling classes. Now let's come to the concept of dipole. A simplest concept of what classically we used to call as a dipole is just a current carrying loop. And let us suppose it flows anti-clockwise by looking from the top. Then our classical definition of poles, this would be treated as a knot, and this is treated. So this particular plane, if you are looking from the top when the current flows anti-clockwise, somehow physicists always like anti-clockwise. So anti-clockwise, then it's the north pole, and the other side is the south pole. And what we used to define as the magnetic moment of a pole, mu in this particular case, will be given by I times A, where A is area vector. There is a how you define the area vector. This is all generally supposed to be first year BTech level physics. So you know what is the mu A. Now, our idea is not to look at the magnetic field here directly. We are not doing a course on electromagnetic theory. We are doing a course on magnetic materials. So I have to transform this particular thing to an atom. Okay. So we transform it to an atom and look from where do we get magnetic moment inside an atom. Alright. And from atom go to solid. That's what's basically the idea. And every time when we go ahead, we find things to becoming more complicated, more difficult. Not all that difficult also. They are fairly well understood now. So when we are talking about currents, the current inside an atom are basically due to the spin motion, motion under quotes, and orbital motion under quotes of the electron. Of course, there is also a nuclear magnetic moment which we will ignore at this particular moment, because that has only a very, very small, their magnitude is small. So most of the magnetic moment arises only from the motion of the electron. Now, in quantum mechanics, people don't want to call it motion because it's all uncertainty principle. You know, you cannot talk of really in orbit and things like that. You know, it's all spin, especially is dealt by relativity quantum mechanics, Dirac's theory and things like that. But on the other hand, people definitely like to talk about angular momentum. So depending upon the state of the electron, depending upon the quantum number of the electron, okay, angular momentum of a particular electron will be known. And if you know the angular momentum, spin angular momentum, orbital angular momentum, I can find out what will be the value of the magnetic moment because of these two sort of under quote motion. Let me use the word motion, not let me write. But you understand that when I am talking about motion, it's only purely in a classical sense, which does not really have a real good sort of quantum mechanical agreement here on that. Okay. So for that, I would like to first express this particular magnetic moment in terms of angular momentum. Now let's suppose an orbital motion. I am dealing it purely classically. Talking of orbital angular motion, the current of that particular thing, if you assume that a particular electron is moving inside a circle, what will be the value of the current will be given by E, which is the charge. I am putting just the modulus sign, so I am not looking at the, of course, it will be negative sign because of the direction in which electron moves. The current sign will be positive, other way, but just to avoid all those things, will be defined by, or let me put here, be more specific, minus. All right, where omega is the angular velocity of the electron. It means the total angle travelled per second. This divided by 2 pi, which is the total angle in a circle, it means total number of times it will traverse in per second. That gives you current. Total charge carried by current. So therefore, mu value, which I have just now calculated, will be given by minus E upon 2 pi omega. Also, I can put vector into what is the area, which is pi r square, where r is the radius of a circle. It's a pure classical treatment. Just to make our way to the magnetic moment of the atom. Now pi cancels out. It becomes minus E by 2 r square omega. And we can write the angular momentum of this particular thing is mr square omega, which is I omega, because it's only one particular particle which is moving. So this gives you a relationship between angular momentum as mu is equal to E by 2m into L. So this tells you that if you knew what is the angular momentum, then you can find out what will be the magnetic moment on that particular current carrying wire. Now this is pure classical, derived on a very, very special case. Now this is what is being generalized when you are going to actual electron moving inside an atom. So we essentially keep the same thing, but now we look at the angular momentum, which is quantum mechanically known by its quantum number. If you know what is the state of the electron, then you know what is angular momentum, you know what is spin angular momentum, and things like that. So if you look at orbital angular motion, this is given by under root L into L plus 1 h cross. This is the total value of orbital angular momentum. Suppose it's particular there is an electron which is moving h cross square. I have put square, so they should not be under root, sorry. You should always catch these things and tell me. I am very happy if somebody says that you made a mistake here. It makes me that you are sort of at least not sleeping. Okay. So if I know the quantum number of electron is L, then this will be its angular momentum. Similarly, spin angular momentum, or let's talk of Z component, will be given by ML h cross. So if there is a particular quantum number of an electron is L, then I know what is its angular momentum, and if its quantum number is ML, then we know that along the Z direction, which is normally the biasing field, like magnetic field, then what will be the component of, so if you want to have what we call as a vector model of atom, the magnetic moment will always be aligned at a particular angle such that its Z component will be this. But remember, for experimentalists, this is more important. Because when we are going to apply magnetic field, this is what I am going to get, not this. So experimentalists have a habit of talking of magnetic moment, which does not mean the top one, which means the Z component. this creates some time of confusion. Now, when you go from your high school or MSc level to research level, because the languages that are being used by people turn out to be somewhat different. All right. Now we can talk in terms of spin. Spin, there is only one half. There is only one possible value of spin angular momentum, that is spin, which is half into half plus 1 h cross square. And if you take its z component, is given by just plus minus half h cross. Now, when I translate this to magnetic moment, the idea of our using angular momentum was to get the magnetic moment on the system. As far as orbital motion is concerned, we can use the same expression that we had derived earlier. But when we want to use spin from relativistic quantum mechanics, there is another factor called G factor also comes in. So, this particular point should be clear. This particular thing, I substitute in that particular expression of angular momentum, which I have calculated, relationship between angular momentum and the magnetic moment, it will work. But if I want to take spin, it will not work. You have to multiply by a factor of G, which is more or less close to 2. All right? Probably all of you are aware of it, but I thought it's better to revise it. So, if I am talking of mu s, this will be given by under root half into half plus 1 G E h cross by 2 m. This G factor does not appear for orbital angular motion. All right. Now, there is a unit of in which we always give the magnetic moments, which is called Bohr magneton. So, all the magnetic moments when we are talking inside the system are always expressed in the units of Bohr magneton. Bohr magneton is defined as E h cross by 2m, and its value is 9.27 into 10 to the power minus 24 joule per this. I will also give its value in CGS system. You will be wondering why. When you go to your research level, especially in the area of magnetism, especially in the experimental magnetism, you get many shocks. And this is one of the shocks. Throughout our life, we study in MKS system or SI system, and suddenly you find all the research papers are you publishing in Gaussian system of units. And this is something you cannot avoid. I mean, we always say that it's very difficult for people to change. I mean, when old people understand only that unit, the new people have to publish. They have to publish in a language which old people can understand. It means you have to use a Gaussian system of units, and that's how Gaussian system of units have been coming out. Okay, I know 1 or 2 papers of mine, referee said, no, please convert everything to SI system of units, then only we'll accept. Okay, we did it, but then also in the bracket we gave the Gaussian system of units, because we want somebody who reading that person to understand. I mean, it's true that even a person like me who's been teaching this particular subject, okay, if you say that I have applied this much of Tesla field, okay, I have to think a little bit to find out what will be the order of magnitude. But if you say so much kilogauss, I will immediately understand, the orders are in the mind. But Tesla, I'll have to convert, so So somehow it so happened that we have always got used to the Gaussian system of units. So this we have to live with. All right. So this is so far as a single electron in an atom is concerned. Now in an atom there is not only single electron but there are multiple electrons. So we should know how to combine this to form the total magnetic moment of the atom. Because if you are talking of magnetism, we are talking of magnetic moments on atom. We are talking of magnetism in solid. Essentially, it's the atoms which are carrying the magnetic moment. Okay, and why atoms are carrying magnetic moment? Because of these angular momenta. And what are those angular momenta? Spin angular momenta, orbital momenta. So that's the line of action. Now what you do, you essentially use LS coupling, which probably you are all aware. I will give you only the final expression. You define a total angular momentum J and express magnetic moment in terms of J. Similarly, the Z component of the magnetic moment also you consider in terms of J. That's what happens. And if you know what is the total angular, first of all, okay, let me go one by one. You know there are different electrons inside the atom. They have different quantum numbers. I must know how to add them to form the total orbital angular momentum, total spin angular momentum. Then I should know how to add them to form K. Okay, this probably I am sure would have been covered earlier also. There is a famous rule called Hund's rule, which decides how these things have to be combined, how these things have to be done. I am not going through that. So I am just going to tell that mu is given by minus G E by 2m J. G is not that G2, but it's another G which plays a similar role, but it's differently defined. Plus steps, as we said, you have multiple electrons inside. From those electrons, you calculate the total number of total orbital angular momentum, total spin angular momentum, total J. Okay, put all these values and obtain a G. That G has to be put here, and with that J, you will get the magnetic. All right. Now, the important thing is that if it so happens that capital L is 0, means total orbital angular momentum as 0, then G turns out to be equal to 2. And if it so happens that it's only orbital angular momentum and spin is 0, total S is 0, then turns out to be 1. Of course, in general, it will have any value. Okay. Please do interrupt me that, if you are feeling you don't understand, or if you are really bothered that I am going too slow. Now, from one atom I am coming to solid. So we know how to calculate the magnetic moment on an atom. Now we are coming to solid. Now in solid you have multiple atoms. There could be various effects of this particular scene in solid, because the neighboring atoms are also going to influence the behavior of electrons and the magnetic moment, etc., on this particular atom. Things like what we call as crystal field, etc., they play a role and could lead into multiple effects. Some of them we list, which is happening, which is very, very commonly seen, especially in 3D transition metals. I hope you know all 3D transition metals, which are generally, which has already 4 s shell filled, but completely d shell. All right. Now, in that case, you find that orbital angular momentum normally does not play a role. What we call as orbital momentum is quenched. So essentially, the total angular momentum is only given by S. Okay, there are certain cases, like for example, in the case of cobalt, okay, it's not completely quenched. There is also a small orbital angular momentum contribution. But the fact is that what we have calculated for an individual atom may not work when you are putting this into a solid. Because other influences like quenching of orbital angular momentum, etc., may start playing a role. So for atom it's perfectly fine, but when you are actually going to solid, things become different. Other important effect which can happen is that these electrons that you are talking may no longer be localized in a particular atom. If we are talking of a band model, which is the correct model, it depends upon what is the width of the band model and what is the spread of the wave functions. What we mean by localized, if the electrons are essentially have the largest probability of being around the atom and very less probability of moving anywhere else inside the solid, it's more or less localized. But if it so happens, which happens for example in the case of metals, in fact some of the most interesting magnetic materials are metallic, iron is metal, then these electrons which are giving rise to magnetic moment are not really localized at a particular atom. They are sort of free, which we call as itinerant. They are itinerant electrons, and that may make all your calculation haywire. Okay, you may get a totally different value of magnetic moment than what you had expected here. But if you are talking of materials which are, for example, like oxides, like ferrites, or many of perovskites, which are basically oxide materials, okay, you find that electrons are generally localized. And then you will find in that case, whatever calculation we have done would work. All right. So we have to take the influence also of what happens into the solids. When we are looking at a generic picture, I will give you the in detail what are the roles of different things in this particular case. So this is what is going to happen. Now we have understood what will happen to the magnetic moments inside a solid. Okay, there is one third effect which I forgot to mention. When you are putting atoms inside a solid, there could be exchange effects, which are purely quantum mechanical effects. Essentially, the example which I used to give is that if a particular atom wants to, let's say, a particular magnetic moment wants to divert it, change its direction. It's a very, very crude way of explaining to students. Wants to divert, whether it's going to affect its neighboring atoms or not. Okay, if it is totally independent, can move around and other atoms don't see what is happening to this guy. Okay, that's a different case. But it could happen that these two are coupled strongly. If you want to move, it's going to influence the neighbors also. I mean, this is a very, very crude picture of it. For example, if you put a lot of balls in an elastic spring and you move one particular ball, okay, then because of the spring forces, other atoms are also going to be affected. So this is in the language of magnetism, it's actually creating what we call as an exchange. An exchange can be of various types. I am sure you would have done many exchanges, issues on exchanges in all the lectures that you have been given so far. All right, so this can also influence. So these are the things which we have to take care when we are actually talking of magnetism inside a solid. Now, we go to the next step. Once we have understood how these magnetic moments are arise and when inside a solid, what type of role can they give. Let us suppose what happens when we apply a magnetic field. About magnetic field also I will talk a little bit later. But let's talk of just a traditional magnetic field. There can be various effects depending upon whatever we have discussed so far. There could be one case of a material of a solid in which inherently the atoms do not possess any magnetic moment, which is quite possible because if all the shells are completely filled, and you can show very easily that if a shell is filled, it does not contribute to any magnetic moment, everything exactly cancels out. Okay, then you apply a magnetic field on this particular thing, they do get influenced by it, but in a different fashion than if there were atoms which had magnetic moments, non-zero magnetic moments. So, such type of materials are called diamagnetic materials. This also I am not going to detail because I am sure you have done it nowhere else, at least in your MSc. Okay. On the other hand, if they have inherent magnetic moment and they are not magnetically ordered, what I mean by magnetically ordered, that they are independent, then we get material like paramagnet. Paramagnet also has a counterpart when you are talking of paramagnetism due to free electrons. Okay, but I am talking in general. Because as I said, when you are talking about metallic materials where there are a lot of free electrons and they are not localized, the picture is somewhat different. A metallic magnetism sometimes or many times quite different from the magnetism inside an oxide material. Yeah. Beg your pardon? Yeah, please repeat the question.
So, some materials are having free electrons, but still they are not considered as metals. So, why they are not behaving
See,
like?
I am not very sure what you mean by free electrons when they are not metals. Most of the, free electron theory was developed for magnetic materials. But
I'm
you know,
talking,
let me complete it. If you are talking of bands, it of course depends on the bandwidth. Okay, how mobile they are, and in principle whether you, in principle they are nothing like exactly free, nothing like exactly localized. They are always intermediate. It depends on how localized and how free. Now, yeah, please go ahead. Now you are asking something. Okay. See, these are two limits. So, one you call it free. Exactly free electron theory is also not correct theory, as you are all aware of it. So, you have to talk in terms of band model, and depends on what is the width, how mobile they are in that case. All right. When you are talking of magnetic ordered materials, then the behavior could be very different. Generally, we consider of three different type of magnetic orders. One what we call as a ferromagnetic, another what we call as antiferromagnetic, and third we call as ferrimagnetic. Ferrimagnetic and ferromagnetic are often discussed together because most, not all, most of the properties are similar, except that their magnetic moments are comparatively small. Net magnetic moments are comparatively smaller because of the antiferromagnetic company. While antiferromagnetism magnetic materials are treated quite differently. In fact, people used to consider them useless materials till about last 10-15 years, until because of the spintronics suddenly there have been a great interest in antiferromagnetic materials. So, basic idea in physics is always that nothing is useless, everything has some use. Okay? You should have capability of finding its use, that's all I would like to say. The thing about magnetic field I would like to talk about it. When we do a course on electromagnetic theory, the magnetic field is defined by a vector B. Like electric field is defined by E. When you are talking about dielectric material, you define another vector displacement, electrical displacement, which is called D. Okay? And if this is a dielectric material, this D and E are related. Okay, magnetism is just ulta. Alright? You define a vector B and you can define a vector which is H. I will give the definition. Like you define electric displacement here, you define here this thing. In electrostatics or in dielectric materials, everyone talks of E, nobody talks of D. In magnetism, everyone talks of H, nobody talks of B. Okay, you look all the papers, other than people who are working on permanent magnetic materials, all the data will be given in terms of H, not in terms of B. Because in magnetic materials, H is the one you control directly experimentally. I am talking as an experimentalist. Okay, in electrostatics, there you don't control D directly, you control E directly. So your data, see, experimentalists will like to give data. I am changing current. This is the field. So with respect to this current, what is the free current? I would like to know what is H. So all the data that we are given is in terms of H and in terms of B. All right. So this thing one should be clear. These are some of the points which people have. I have found students have a lot of doubt. That's why I am spending time on this particular thing. Okay, there is a B field and H field. Experimentalists will always talk of H field. Many times they give different names to B. Okay, and then if you look again at Griffith, he shouts at all the experimentalists saying that this is useless. Field is only B. Field is not H. You can call H by whatever name you want, but field is B. But if you talk on the experimentalist, field is H. Sorry to say, but this is the way. I mean, many times, see, like mathematicians and physicists don't agree. What physicists call log, mathematicians call ln. All right. What we call theta phi, they call phi theta. So I mean, they're never an agreement. This is the way science has. Okay. The relationship between B and H for free space is very trivial. It's related by a fundamental constant. So either you can talk in terms of B or in terms of H. It makes no difference. But when you talk in terms of magnetic material, it does make a difference. H is defined as M. We have already defined as the magnetic moment volume when we apply field. Okay, sorry, I have not defined it. M is the magnetic moment totally developed when I apply magnetic field. Developed per unit volume. In Gaussian system of unit, this is in Gaussian system of units. Is there any questions? Anything which you would like to comment? Now, having understood this, I come to the most basic thing which an experimentalist look for when you are doing a magnetic material is MH loop, what we call as a hysteresis. We will also plot BH curve about that, especially people who are working in permanent magnetic materials. I will briefly mention about that. But as I say that the entire effort of material scientists would be over if I could shape the MH loop to the desired shape that I want for an application. All of our effort is only to control this MH loop. That's the basic. I mean, probably I'm overexcited to say that statement, but that in principle is correct. And I will give you an example of what I mean by that. So essentially it means that if you're starting a material with a demagnetized state, what you go initial magnetization curve, and then it saturates. Then when you reduce the field, it does not follow the same path after some time, and it goes back like this, and then saturates in the other direction. I'm sure you would have seen this particular type of loop, symmetric for most of the material. This is your MH. There are multiple points on this particular loop which are of interest. So let us list those points and see what are the utility of these points. First is this, which you call MS, saturation magnetization. This essentially tells you that when you apply a particular field, how much is the total magnetization that you are going to get. Remember, this magnetization that you are going to get will depend on mu z, not on mu. Okay, so let's be very clear about the thing. But we always talk of magnetization and mean mu z, because whatever is mu, I'm not going to get it by map. See, there are certain measurements in which you will get actual mu. Okay, especially if you are doing critical exponents, etc., all those things, susceptibility measurements. But as far as magnetization measurement is doing, using loop, you are getting saturation magnetization, you are actually determining mu z. Now it depends on small magnetic field. If you apply, get large magnetization. All right. Then once you have removed the field, how much magnetization is retained? This is called MR, remanence. So one point is MS, another point is MR. We normally put MR upon M. This particular issue. Third is how much field you require to bring magnetization back to zero. This is called coercivity. Fourth point, which is of importance, is when you are starting from demagnetized state, what is the slope at this particular point, which we called initial susceptibility. Susceptibility, see, again, let's be very clear. The terminologies are very different, so you should be very clear. See, if you ask generally a person what is susceptibility for ferromagnetic material, everyone will say zero, infinite. Because even with H is equal to 0, you can get magnetization. Domains are always magnetized saturation, as I will be discussing later. But when we are talking, we mean actually this magnetization that we are getting, which is on so many other factors. So for us, we can still define a susceptibility depending upon how much magnetization I have got. It's not a fundamental quantity. It's a quantity depending on material. If the same material you make in a different form, if the grain sizes are different, susceptibility could be different. So these are not extrinsic property, but extrinsic properties. But they are important properties because if I want to use this particular material, I have to control it. All right. There's some other thing which, two more things. One is, let me just see. Initial susceptibility. Fifth is what you call as a switching field distribution. It's called SFD, switching field distribution. It essentially tells that this particular loop, how does it fall here? Okay. For example, the shape of the loop in this third quadrant could be like this. This is more like what we call as a square loop, which goes in one direction, switches into other direction. All right. Other thing, it moves slowly. Third thing is still moving very, very slowly. It comes to the same point, but how does it come? How rapidly it comes? This is what is called switching field distribution. This is very, very important for magnetic recording. Because, I mean, you know, those semiconductor memories are picking up, but still your hard disk that you are using in computer is still magnetic material. And if you want to write a bit, okay, there has to be a magnetized region separated by a non-magnetized region. And if there is a slow change there, your bits will not be very precise. So you want a material like this, so that you write a bit, it's magnetized, not magnetized. The larger is the region in between them, poorer will be your recording density. All right. So this is extremely important for recording, guys, how you make this particular portion of the loop. All right. Now, just to give an example, if I am using a permanent magnetic material, okay, then I want that once I remove the magnetic field, remanence should be as high as possible. All right. Otherwise, you have magnetized it, but as soon as you remove the magnetic field, the magnetization is essentially called to, let's say, 10% of its value. It's not a good permanent magnetic. A good permanent material is where you have removed the field and still significant amount of magnetization remains. You require remanence to be large. Then you want also coercivity to be large. Because it should not happen that you bring a tiny magnet and the entire magnetic moment becomes zero. All right. So these are materials which are called hard magnetic materials. Hard magnetic materials which have a large remanence and large coercivity. For example, in recording, if we take, if we want to take a recording medium Of course, there we are talking much smaller value of coercivity, etc., whatever it is. Okay, but that also once you write a bit, that bit should stay, and should not happen that you bring a tiny magnet and your entirely hard disk is erased. Okay, so you want large coercivity. This is the typical signature of hard material. On the other hand, soft magnetic materials are just opposite. You get a large magnetization, but you remove field, it goes zero. Suppose you are using a recording head. Okay, now you have magnetized it, it is writing, but if you remove the magnetic field, it should not still remain magnetized. Otherwise, it will keep on writing. Alright, so you want remainers to go to zero. So, as I am telling you, just to make you appreciate that these are the things which are very, very important for application point of view. Each point of these things are important for application point of view. Essentially, I mean, saying large or smaller, these are not very scientific terms. It depends on, again, type of material. How hard, how soft. So, these are the things which have to be controlled. Depending upon an application, you have to control your MS loop. If you are able to control your MS loop, then essentially, as I said, you have solved most of the problems of the. But there are other problems also like temperature dependence. I mean, there have been cases where you have found excellent magnetic material. Okay, but you raise the temperature by 20 degrees or below 20 degrees, all the properties are lost. They are not useful. If you want to have a device, it should work in Siberia as well as in, let's say, Sahara Desert. So it should at least go to the temperature range of minus 50 to plus 50. It should be stable. There are many other criterion also. So that's why I am saying it's probably an overestimate saying that MS loop control is the most important point. There are many other points. I mean, I know of the materials, we have worked on the materials which are considered excellent material. Only because of their temperature dependence, they could not be used. Because the temperature dependence was very bad. Just change by 10 degree properties are totally different. And the last thing that I have not mentioned is BH mix. This is what generally the hard magnetic people use, permanent magnetic people. They do not plot MH, but they plot BH. And here they try to fit maximum area, maximum rectangle, which you can fit into the third quadrant, which they call as BH max. So these are the various points which are important for MH. Now, how to control MH? How MH arises? I mean, should I have some questions now, because now I have already taken 1 hour 20 minutes, or would you like to continue? Let me have some question. If it's not there, I'll continue for 5 or 10 minutes more.
Yeah, come on. Let's have some doubts. The other person might have same doubts. So. That's a good idea. Anything you want repeated, kindly tell.
If you plot BH curve, it will not saturate because B is equal to H plus 4 pi m. As you keep on increasing H, it will still continue a linear slope. It will do a better job. Now, this is the third quadrant. You try to fix a rectangle wherever it is maximum curve. That's what is called BH max. Essentially, it tells you what is the energy stored inside a permanent magnetic material. So, larger is the BH max, better is a permanent magnet. I will talk a little bit about in some of my little lectures about permanent magnetic materials, just to give you an idea which are the materials and what are these orders of magnitude.
Anything else? Anything you want repeated?
Okay, let me take 5 minutes more. Now, why a particular shape of MH loop arises altogether? Fundamental things. What happens in magnetic materials, ferromagnetic materials? When I say ferro, it will include ferri. They are magnetic domains. Probably you are aware of the molecular field theory, which can be seen. So, it's not only a theory, it can be very easily observed, which are always magnetized to saturation. Now, the fact is that you can see a material in a demagnetized form is a result of orientation of these domains in certain pattern, which makes energy lowest such that net magnetization cancels out. All right. Now I apply a magnetic field. It's no longer energetically favorable for these domains to remain where they were earlier. Now two processes can happen. Either domains which are favorably inclined towards the magnetic field, they try to grow in size. Okay, or if your field is large enough, they can rotate. And what they will do depends again on the energies. And energies are not all that simple. They are reasonably simple in terms of a single crystal material, but once you go to polycrystalline materials and these days to nanocrystalline materials, the energies are essentially very, very difficult to evaluate because there are so many factors which are involved. I hope you know the difference between polycrystalline, nanocrystalline and amorphous and single crystal material. Okay, but let us start with the energies which are there in a single crystalline material. And one of the most important energies which I will discuss first, which is probably the one which is controllable somewhat easily, is the magnetic anisotropy. And there are multiple types of magnetic anisotropy. I think I will just discuss anisotropy and then we'll close. Other energies I will discuss in the later lecture. Okay. The first and the foremost important is what we call as crystalline anisotropy. Crystal by its own nature is anisotropy. 100 direction is never going to be same as 111 direction, irrespective of the type of crystal that it is. Let's take cubic. If you are taking along 100 direction, you see atoms at a distance of A. If you are going along 111 direction, you are seeing a distance of root 3A. Okay, band structure, everything is going to be direction dependent. Okay, therefore magnetic properties are also going to be direction dependent. So there are certain directions in crystal which are favorable. Magnetic anisotropy again arises because of mixture of spin orbit coupling and crystal field and things like that. Again, probably this might have been taught earlier. All right. For example, if you take iron 100 is in easy direction. But in a crystal, cubic crystal, there are 6 equivalent 100 direction. This is 100, opposite to that is also equivalent 100. Okay, this is also, this is 010, but it's equivalent 100. There are 6 equivalent 100 directions. All of them have to be easy. Okay, you cannot differentiate between 100 and 001. Because what you are calling x-axis, you could have called y-axis. Alright? So, while 111 is hard direction, it means if you want to magnetize iron along 100 direction, it will quickly magnetize. With a very small field, it will magnetize. But if you want to apply 111 direction, you have to keep on applying field until it overcomes that anisotropy and then magnetize. Nickel is just opposite. 111 becomes easy and 100 becomes hard. In fact, some of the materials which shows the largest anisotropy are hexagonal materials. For example, cobalt, where C axis is easy axis and the entire plane is a hard plane. Alright. Now, these are because of their crystalline nature. These are intrinsic to it. Okay. I am not giving mathematical expression. In my notes, I am giving the mathematical expression. If you want to see, read more about it, you can do it. Another is what we call is a stress anisotropy. also very common and very useful. There are many materials in which this particular thing has been used favorably to make devices. There are many materials which are what we call as magnetostrictive, where you apply pressure, then isotropy direction changes. Especially when you are talking of ultra thin films, it's completely easy to stress them by putting a substrate which is slightly different, having lattice constant or whatever. There are ways of doing it. And people have done in the case of by implanting, you have a lattice, you put some ions inside this, so they expand the lattice, and because of that thing, an isotropy changes. Okay, they are essentially stress induced anisotropy. Third thing is shape anisotropy. This is related to magnetostatic field. If you have a material like this, let's say thin film, if you want to magnetize it in this direction, normal to the film, it will be difficult to magnetize it, because the pose that you are going to create will be too far, too near to it. If you magnetize it like, it's much easier to magnetize, just because of the shape. There are certain expressions which are given, which I will be discussing later. So, it's just because of the shape, it's normally it's easier to magnetize in the longest direction. This particular isotropy has been used, probably you would not have been seen that generation, but my generation has seen tape recorders. Have anyone seen tape recorder? Some, I think we are old, who are seen the tape recorders. There used to be tape recorders where you used to record earlier thing. They used to use particulate media, and they use essentially the shape anisotropy, needle shaped particles, which will have a large anisotropy, and that used to increase coercivity to make them to save the recording. So shape was being used as an anisotropy. So I mean, these are various ways in which you can change, as I said, loop and. Fourth is surface anisotropy. Surface or interface anisotropy, that's a better word. No material is infinite, always going to have an end, and the material which is at the end, which will not have the same experience or same environment as the rest of the material, which effectively acts as an anisotropy. In ultra thin films, the shape anisotropy has been used to change the loop shapes. I'll give you some examples later, depending on the time that I have, where they have made ultra thin films and use essentially the surface anisotropy to dominate over the crystalline and another anisotropy to change the loop shape. Because as I said, our idea is to change the loop shape to a desired shape. That's what we want. All right. And two anisotropies, then we close. Growth induced anisotropy, which is the most, what do you say, mysterious anisotropy. They are materials, especially in thin film form, this is very common. Just by the method you deposit them, you create certain anisotropy. You do not know the reason. One of the famous example was 1973 paper by Chaudhary, Praveen Chaudhary and other group in IBM, wherein gadolinium cobalt films which were amorphous, because there was no crystalline order, they could show very large uniaxial anisotropy. Uniaxial anisotropy means single direction anisotropy. Very large uniaxial anisotropy. Okay, supposed to be random. There is no other anisotropy present. And that was coming only when they were depositing by DC sputtering. The same material is exactly same composition deposited by some other technique. You will not get that anisotropy. And you will get consistently with that deposition only. So that particular method of deposition was creating something which is definitely not isotropic, which probably at least the instruments at that time could not detect. I mean, there are half a dozen theory of why there is an anisotropy in gadolinium cobalt. One was the famous case of magnetic bubbles. There was a time when I was postdoc, magnetic bubble was the most fashionable thing. I'll talk about magnetic bubbles later in one of my lectures. Okay, there the anisotropy that was required came from growth-induced anisotropy. That was single crystalline material. Two different contrasts. Single crystalline material, growth-induced anisotropy, amorphous material, there is growth-induced anisotropy. One does not fully understand. There also one thing that rare earth atoms are having some sort of favorable way by which this anisotropy is created. Because the same method, same material, you use a different epitaxial. I mean, that's the epitaxial growth, which is very good growth, very high quality. But still there is an anisotropy. Same material deposited another way, you don't see that anisotropy. All right. The last which I will talk about is surface. No, there is forgot the name. This is a unidirectional anisotropy. It's possible to create, see, normally when there is a particular direction of easy axis, opposite to that is also an easy axis. But it has been possible by magnetizing sample to create a direction which is only in one direction and opposite to that is not easy. This is what used to be called exchange bias materials. Used to create a bias inside them so that essentially an anisotropy acts only in one particular direction. So when you measure MS loop, they always turn out to be shifted. They are not symmetric about X, Y, and Z. So these are about the anisotropy. I will talk about other energies and what is their influence on the loops. Okay. Any feedback, you are most welcome. I'll be happy. What I am planning, second lecture, I am going to talk about crystal structure, which I'll do PowerPoint, and talk about some crystals. Third lecture, again, I will go back to these things. Then I'll talk about some of the experimental techniques which we use, how to interpret the results and things like that. That's how I am. Any feedback, howsoever negative, is welcome.
Questions, comment, please. Yes, no. Question? No question. Okay, good. So we'll break and we come back at, what is it?
2:30?
2:30, I think.